Hi everyone. How do volumes change under a parameterization map? Remember, to integrate is to take the volumes times the values of the function, and so we're going to need to know how volumes change soon. Okay, so explain this. For a parameterized surface, some surface inside of three-dimensional space. That's part A. Okay. A parameterized surface is the image of a map. What kind of a map? Let's give it a formula. Let's say G from, well, it's a surface, so it has to be two-dimensional. And we throw two-dimensional space into three-dimensional space, giving a surface inside of there. Okay. Picture. Here's our input space. Here's our point P. And G maps us over into three-dimensional space. And I draw the same thing every time because then it's easier to understand what's happening. Here is the image of this map. So, some square here becomes this curvy, weird, shaped thing. Okay. And, somewhere is this point G applied to P, G of P. Okay. Now, what happens is that a small square here becomes some curvy square here. Let me say it in words. A small square near P becomes a curvy square near G of P. Okay. Now, what happens though as we shrink our square? Well, the derivative thinks the square becomes a parallelepiped, or in this case, because it's going to be two-dimensional, we'd call it a parallelogram. But in general, for any dimension, like later we're going to do this, three-dimensional in R9, we'll call it a parallelepiped. But whatever it is, it's some sort of flat object where all the sides are parallel and linear and straight. In this case, two-dimensional. Okay, derivative thinks the square becomes a parallelepiped. And we know how to measure the volume. So the question is about volumes. How do volumes change? And we know the volume of parallelepipeds is, and now here's the formula, square root determinant of the gram matrix of, well, whatever the vectors are that give us of some, vectors. Let's take 2 because we're going to have actually a parallelogram, which is 2 vectors. It'll be like this and this. There's the parallelogram. So we need the 2 vectors that will span it. See how the 2 vectors. In fact, here is the vector, the first plus the second is the diagonal. Okay. Okay, so we're almost there. And so what do we need? The vectors W1, W2 spanning creating this parallelepiped come from the columns of the Jacobian matrix. The Jacobian matrix let's call them, we could name them anything we want. Let's say W1 is dg at P applied to E1, and W2 is dg at P applied to E2, okay? And in this case, W1 is literally like some a vector with 3 components, 3 numbers. We have plugged in at the point P, and we've plugged in the vector E2, and we get out just that one column, the second column, or the first column. Okay. And so, we can actually compute that. And so how, the question is finally, how do volumes change under the parameterization map? So as we take smaller and smaller squares, the derivative gets better. So in particular, and here's the important thing, a square of volume 1 would be the square spanned by E1 and E2 becomes volume, well, W1, W2, and the volume there will be square root determinant gram matrix of W1, W2, where I had to actually tell you what W1 and W2 are, okay? And so a square of volume epsilon, very small, of very small volume, let's say epsilon, this is a Greek letter. You can call it whatever you want. You could call it S for small. Becomes volume roughly equal to, well, S times just this very small number, like maybe it's 0.001, just this number multiplied by square root determinant gram matrix of the columns of the Jacobian matrix. There it is. And so we see that, the square E1, E2 clearly becomes the parallelepiped W1, W2, as we explained in the last problem. A square of very small volume S is really very, very, very close to exactly that parallelepiped. Well, multiplied by S. Okay. And so the factor, the change of variables factor, this is the change of volume factor. Factor because it's what we multiply by. If the volume was S, we multiply by this. If the volume was 1, we multiply by this. 1 times that. Okay. And that's it. That's the end of part A. Let's do part B. Part B is actually easy. Explain this for a parameterized 3-dimensional manifold M in R9. And why would we want to do this? Well, here's an example. Cryo-electron microscopy is, for example, in 2017, the Nobel Prize in Chemistry was awarded to people who developed this to determine, the structure of some molecules. And in order to actually do this, what you do is you sort of like freeze these things, these molecules, and they're going to be frozen in some random rotated version. And you freeze them again, and they'll be in a different random rotation. And you freeze them, you do this hundreds, thousands of times, and you look at all of these frozen molecules, but they're all rotated in different ways. So you have to average over the group of rotations, and the group of rotations of space is a 3-dimensional object inside of R9. And in order to do cryo-EM, you need to average out those rotations of your molecules. And to average them is to take a weighted sum by volume. In other words, you would need to integrate over this thing. And so, fear not, it's very easy. Let's do part B. Part B. It works the same, exclamation point. The map is, well, it's a 3-dimensional object, but living inside of 9-dimensional space. Right, what did I ask? I asked, explain for a parameterized 3-manifold inside of R9. Okay. And we use the 3 columns of the Jacobian matrix, of DFP, right, of the derivative. And so then we just do the exact same formula. Square root, determinant of the Gram matrix of, well, in this case, there were 3 input variables. So there are 3 columns of W1, W2, W3. And this equals the change of volume factor. Volumes change by this amount. You multiply by this number for exactly the same reason. And that's it. So, what's W1? W1 is DFP of E1. And, in this case, the output space is 9-dimensional. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. No problem. Okay, that's it. The Gram matrix will be a 3x3 matrix. And you can take the determinant of a 3x3 matrix, and you can take the square root of a number. And we have done all of this before, and now you can do cryo-EM. You can average over the group of rotations, which is a 3-dimensional manifold living inside of 9-dimensional space of 3x3 matrices. Okay, that's it. That's all. Okay, so you see part B, I just really wanted you to say that what are the sizes of W1, W2, W3? Well, they're 9-dimensional vectors. The Jacobian matrix of the derivative has, 3 columns. Because it's the same formula. And all you need to do is make sure that you tell me what are the sizes of the input and output. How many columns of the Jacobian? What are these vectors, W1, W2, W3? How big are they? They have 9 components. Very easy. It's wonderful. It's this one formula.